more about floating point, I just want to go back and remind you that this is written and exists and has been fairly well debugged. And there are there's a couple of reasons for doing this. One is a few of you may want to use floating point for the solver. And also, if you're going to do DSP for a final project, there are some kinds of filters that are easier to write with floating point than they are with fixed point. In particular, second order sections, which are a factored filter in which high order infinite impulse response filters are rewritten as the concatenation of second order sections. Did that sentence make sense? Okay. So, if you have let's say that you want to make a sharp cutoff infinite impulse response filter where frequency is this way and log amplitude is this way, then to get sharp cutoff, you have to have a large number of poles in the filter, right? You have to, RC sections, however you want to think of it. The more poles you have, the more precise the arithmetic has to be, because the way you get a sharp cutoff and a flat top is precise cancellation of terms near the corners. That means to do accurate high order filters, you need to carry lots of bits and use lots of hardware. And so it could occur to you, as it occurred to engineers in the 60s or so, that there might be a better way to do this by simulating say a sixth order filter as the concatenation of 3 second order filters. So there's 3 two-pole filters in a row. Can they be matched in such a way as to produce a 6-pole filter with sharper cutoffs, while at the same time requiring less accurate arithmetic? The answer is yes. So you can show that by factoring a 6-pole filter or an 8-pole filter into 3 terms or 4 terms, that you can reduce the number of bits required from something like 32 to something like 10. That's huge in terms of multipliers. So it turns out that this particular kind of filter requires a scaling multiply between each stage and even one at the input, in which all of the numbers, all of the signals are scaled by a number like 10 to the minus 4. That's hard to do in fixed point, but trivial to do in floating point. So a high order filter that's been written as an SOS, second order section. So high order filter that's been written as second order sections is easier to write in floating point than in fixed point. And I built some of those at one point using 9-bit mantissa, and they worked just fine. So this version of the floating point that I'm talking about right now has an 18-bit mantissa, or more formally a significand, and 8-bit exponent and 1 bit of sine. Supports a floating point add in 2 clock cycles for pipeline for faster execution. Although I rewrote it as a combinatorial add to see how fast it really was combinatorially, and it runs at something like 100 megahertz combinatorially. Requires about 550 ALMs per adder. Whereas a multiplier runs just fine in 1 cycle, requires about 80 ALMs and 1 DSP unit, which which is a lot of logic, but you don't have to build it. Most of the logic here for adding comes from the fact that if you have two floating point numbers, 3 times 10 to the 6, 2 times 10 to the third, to multiply them is easy. You multiply these, you add these, you're done. To add, you have to normalize these to the same exponent, do the add, and then renormalize to the correct value. Whenever I say normalize, I'm meaning shift here. So there's a big shift operation that has to be done at the input of the add. Then you have to do the add, which is trivial. And then you have to do a big shift to renormalize at the end of the add. So it's all the normalization stuff you have to do because of the exponent encoding that makes this such a big and slow process. These particular students wrote floating point inverse square root. Oh man, that's obscure. Why? Well, it turns out it's easier to write than a direct square root. But they wrote a floating point inverse square root. It has a pipeline, I believe, 5-stage pipeline. Negate's easy. You flip a bit. Absolute value is easy. You zero a bit. Compare is straightforward, except you have to look at both the significant and the exponent. Floating point shift just does a multiplier divided by 2 or power of 2. And there's integer to floating point to integer, so that you can output audio, because the audio codec expects integers and produces integers, has integer output from the audio ADC and takes integers in to produce audio back through the DAC. But there's 2 routines that also run on the HPS, which convert a float to this reg27 internal format, and takes the reg27 format and takes it back to a float. It's pretty well worked out, works nicely. I used it to build a floating point version of the digital differential analyzer you built in lab 1. It's quite stable, it's bulkier, it's slower, because there's just more arithmetic in each step. It's bigger, a lot bigger, but the results are rather nice and accurate. So there's some examples of actually using it if you find you want to use the floating point. Also, though, if we go back down a little bit further in this list, back down into the dark old days of the DE2 stuff, that there's a section on DSP which includes a bunch of implementations, but specifically using second order sections. So this code, the Verilog here, uses a custom floating point. In this case, that was 18-bit, not 27-bit. But since it's all in terms of FP multiply and FP add, you can just substitute floating add, the 27-bit floating add and multiply in there, and have a executing infinite impulse response floating point filter. For audio work, it doesn't make sense to use a parallel pipeline. The canonical model for building a pipelined IIR filter. Yeah, you know what I mean by IIR versus FIR? Yes, okay. An IIR filter is you have some input, you have some indices B, and you have some then feedback from the output, which is fed back in through some coefficients A, and this particular structure minimizes the depth of the adds and maximizes the speed of this device. You can easily run one of these things at RF rate on this FPGA. So you could do about an 80, well, depends on how many bits. If you do 18-bit, you could do 180 tap finite impulse response filter, or 280 tap FIRs, completely in parallel at bus rate, so 150 or 200 megahertz, if you wanted to do some sort of baseband processing of some fast signal. But that's gross overkill for audio, because nothing changes faster than 48 kilohertz. So using a parallel structure like this, in some sense, is just a waste of multipliers. And so, the audio filters that I've been building over the years have all been sequential state machines that take 8 or 10 or 15 steps to do about up to, say, 6 poles of filtering. Now, because they don't take much resource, you can build a lot of these things running in parallel. I figure you could do a few thousand poles of filtering on this architecture before you run out of multipliers. Then the question is, what in the hell do you do with all that filtering capability? Well, if you can build a bunch of fast filters, why bother to do an FFT? Why not just build a bunch of narrow filters? And the advantage here is that you get to change the bandwidth of each filter so that the log F, the bandwidth is a constant fraction of the frequency as opposed to a constant bandwidth like it is with an FFT. So it's a constant fraction rather than a constant value. And that can make a really nice continuous time filter, frequency analyzer, because you don't have to segment the data and then FFT that segment and then segment the next data. You generate a new value of the filter output for every audio cycle in parallel. This is particularly useful for like speech analysis, because the way you perceive speech, the way you perceive sounds, is approximated as a group of filters whose spacing at low frequencies is linear in frequency and with constant bandwidth, and at higher frequencies becomes a broader distribution of frequencies. This is called a Mel scale. And you can, by breaking voice down into about 30 channels, 30 frequency channels, you can completely reconstruct voice from about 30 sine waves. The result is slightly otherworldly. I think I have an example here. This is, I just ran this in MATLAB, but you could run this on the, let's see, there's the audio connection. Audio connection. Maybe that. Yeah. So this is a 30 channel, my voice.
1, 2, 3, 4, 5, 6, 7, 8, 9, 0.
So that's reproduced by feeding my voice into a filter bank of 30 filters every 16 seconds, getting the average energy output of each filter, and only transmitting those 16 numbers every 16 milliseconds. That's one number per millisecond. Only transmitting those 16 numbers to the reconstruction, where those numbers then, or 32 numbers, where those numbers control the amplitude of a sine wave at the center frequency of the original analysis channel. So that's a superposition of 32 pure sine waves. And that's why it sounds kind of vaguely organ-like. There's no sort of triangle wave or raspiness or anything in there. But it's understandable, weirdly understandable. You can get some understanding down to 3 sine wave.
Is this how you would do something like a vocoder?
This is a channel vocoder. It's exactly a channel vocoder. Now, the interesting thing is, what if I play that back in a different, if I just take all the frequencies and instead of using the frequency I use to analyze, I bump all the frequencies up 10%. I've changed the pitch of my voice 10%. I think I have an example of that on probably on the 4760 page where I was playing more with this. Somewhere, but you can on that site you can do pitch shifting this way, and it's pretty nice because it's continuous time. There's no blocking, there's no framing due to FFT. It's continuous time, and so the results sound pretty good, if somewhat sing-songy. Now, what I haven't tried is, what happens if you dither each of those frequencies, each of the reconstruction frequencies, just a little bit within band? Would it sound more like a real voice? I don't know. Because there's sort of random components mixed in that way. What did I do? I did some parametric tried varying the number of components that were kept. Oh, there it is. Yeah, all right. So this is the original thing.
1, 2,
Yeah.
3, 4.
All right, you get the picture. Now we'll go to 15 filter channels. Or 8 channels. I would argue that's not actually understandable. This version is pitch shifted up 1.75 times with 30 channels. The three chipmunk.
Was 30 the most you were able to get on there?
Oh, no, no, that, you can put hundreds on there.
Okay.
But what I was interested in for the 4760 page is how few could you use to and therefore compress speech for playback, so that you wouldn't need to use as many, as much bandwidth to transmit the data or store the data. For doing a speech vocoder on FPGA, you'd probably go to more than 30 channels, where you have a ton of CPU power, and then do interesting things with it. Also, a Mel frequency bank could be the first step for input to a speech recognition algorithm, or for a speaker recognition algorithm. Because the first step in doing speaker recognition is to take the Mel spectrum and then do the FFT of the spectral components. Oh, what? So you're looking for periodicity in the frequency domain. Makes my head hurt just thinking about it. So now if we go back and look at what one of these filters looks like, and I've written all these for the DE2, and the code is exactly the same because it's just Verilog. The stuff that has to be hacked is the audio codec, which is worked out here. But the basic there's a bus master for reading and writing from the FIFO. We started out, of course, by just reading from the FIFO to get reading from the FIFO, or get the FIFO space, and then write the new sample to the FIFO. But there's one added thing here now, and that is to read the stereo from the audio input, because this is doing a loop back, taking audio in and putting audio out. So this code then reads the input ADC from both channels. That's the usual structural coding stuff. And where's the filter?
I think it's above the bus master.
Above the bus master, maybe.
Well, maybe it's not
That's
fine.
weird. Wait a minute. Example, it's just, oh, that's a loopback configuration. No wonder, there's nothing, no processing in it. So, let's go to one where we actually do some processing. So the first thing I did was to make sure I could actually read the channel in and get it back again. So the filter is going to implement the MATLAB direct form 2 transposed that we all know and love from MATLAB, which uses the filter command in MATLAB, where you have that an output value is equal to B1 times X1. That's my least favorite feature of MATLAB is one-based arrays, but never mind. So there's a series of input terms. So the top line here is a finite impulse response filter. When we add any term on the second line, it becomes an infinite impulse response filter. And what I implemented here was just a second, a two-pole filter. And the way it works is to define a MAC operation, a multiply and accumulate operation, which is to use a multiplier, hardware multiplier block, to multiply some coefficient times some value, because it's a linear filter, it's always a coefficient times a value, input value, and then take this product and add it to the old MAC output to make the new MAC input. doing a running sum effectively of terms. And then you merely step through each term. So we zero the old MAC value. We retrieve the B1 coefficient. We take the F1 value, the first sample value, use the audio in, which is 16 bits, sine extended to 18 bits, and then, and also copy it to XN because we needed it for another one, for another value. Then go to the second state, where we take the new MAC address, put it into the old MAC, set coefficient to B2, set F1 value to X minus 1, go to the next state, just step through and do each add, multiply and accumulate 1 per step. So this is really a really simple CPU that has an add operation and a multiply operation. And you can think of these as, each one of these states is basically an opcode that goes through and does a multiply and accumulate operation. Reads registers, does a multiply and accumulate. Then when you get all done at the end, you have to renormalize this for audio output, do the state machine update for the various internal variables, and tell the system then wait here until there's new audio input. Since it sort of looks like a CPU, at one point, back in the bad old days, again for DE2, I wrote the world's stupidest CPU that was meant for doing digital filtering. So these are the only instructions in the ISR: add, store, load, jump negative, out, in, multiply, and shift left. That's all you need for a multiply and accumulate. So it was an 8 instruction computer, which may or may not be Turing complete, but I didn't care, because all I'm doing is to step through a series of multiplies and adds. But this allowed a kind of an easier writing assignment for the code, because then, instead of writing some ungodly Verilog, all you had to do was write an assembler program. So these are constants that are stored in memory in a data section, and then a code section actually implements the multiply and accumulate as assembler code. Had to write an assembler, but that turns out it's not so bad in math now. So you can fairly easily write a CPU that'll do audio rate filtering for you, and that's completely general. You can do any filter you want. It does also suggest that it's not very hard to produce a custom CPU that will do anything you want with any instructions you want. Why did I use multiply and add? Why did I just make a MAC instruction? Maybe I should have. Why don't I make a CPU that has an instruction which says compute new drum node, right? You can write a very small CPU with 5 or 6 instructions that will do a very limited set of very useful things at high speed. This will run very fast because it's one-page code. So there's various implementations of DSP in 18-bit fixed point, 27-bit fixed point, 18-bit floating point, using CPUs, using parallel architectures. Over a period of years, I've written all this junk down. You're welcome to use it, of course. If you find yourself needing to build filters, start with mine. I think doing some speech analysis with a filter bank would be interesting. fairly big filter bank. There's very small CPUs that are out there if you really want to build small CPUs. There's one called J1, the J1 4th CPU. J1 4th. This is written for a camera. It is an addressless CPU. You do only stack manipulations, but it's extremely small, and it's in open source Verilog. Be fun to port. There's also, you're familiar with RISC-V? You've heard that around. There's a small implementation of RISC-V called Pico, P-I-C-O, RV32. That is a cut down version of the RISC-V that I believe still runs the GCC toolchain. And I wrote a stack CPU also if you want a very odd architecture. I wrote a stack CPU that would ran its own stack language. I called it Pancake Stack Machine. And so the compiler was called Syrup. And there's an assembler which has a bunch of really obscure commands, stack commands. But the Syrup compiler kind of does what you'd expect. So you can if you use the name if you use a literal, it pushes it on the stack. So this says push 0 on the stack and then transfer it to the memory location count. While forever do, quote enter puts this string on the stack, then put string get hex character line feed, pukes it out to the terminal. And count 1 add equals count is count equals count plus 1. Yes?
So if you just want a processor, wouldn't you be better off just using the HBS, which is already there? What's the advantage of implementing this in the HBS?
So the advantage is you can build a ton of these little things. If you need an array of, say, CPUs to do, say, a drum, or a Mandelbrot set, you can write CPUs all over the place. They're small, and therefore they are fast.
So how many of these things can you get on that FPGA?
This one, I think it was, I believe it was, about 1,000 ALMs. So there's 32,000 ALMs. You could put 32 of them on there. And they were running about 75 megahertz. So, 1 week from today, 5-minute final project presentation. Anybody want to talk about their idea? I saw your eyes light up when I said speech analysis. Yeah.
Oh, yeah. Oh, that's competing.
I see. Okay. So that's a possibility.
Yes.
Okay. Anybody else want to talk at all? Okay, let's go back to the lab. What do you want to hear about now? What do you want? If the obvious topics are things that are going to be useful for final projects, but what would those be? There's lots of possibilities. You want to hear more about head-related transfer functions? Would you prefer to spend the rest of the semester in the lab? Write me some opinions on Piazza. Let's see what people say.